Hello, everyone. Thank you for joining us for EE Power Day, brought to you by EE Tech Media and eepower.com, and sponsored by Mouser Electronics. I'm Dale Wilson, the Director of Engineering and Content for EE Power, and I'll be your moderator for our next session. Before we begin, I'd like to announce our giveaway winners from the previous Qorvo keynote session. Congratulations to Daryl Hambley and Bob Williams. You will receive an event t-shirt and wireless charger, courtesy of our friends at Mouser Electronics. We'll contact you next week after the event to ensure we have the information we need to send you that giveaway package. Now on to our next session, which will be covering high power switch mode power supplies, when to use silicon, silicon-carbide, or a gallium nitride, and is brought to you by Infineon Technologies. Let me tell you about our distinguished presenter. Dr. Gerald Deboy is a fellow at Infineon Technologies, where he leads a system innovation group that specializes in new applications and technologies for power electronics with a focus on wide-bandgap semiconductors. Dr. Deboy received the MS and PhD degrees in physics from the Technical University of Munich. He is a senior member of IEEE and has served as a member of the Technical Committee for Power Devices and Integrated Circuits within the Electron Devices Society. He has been awarded more than 100 international patents, has authored or co-authored more than 100 technical papers, and contributed to 3 student textbooks. Following the presentation, we'll have a live Q&A with Dr. Deboy. You can submit questions at any time during the session using the chat box on the right-hand side of your screen. Thank you so much for joining, and with that, I'll hand it off to Dr. Deboy for the presentation.
Thanks a lot for the introduction. It's my pleasure to talk today about the use of silicon carbide, and gallium nitride-based power devices in high-power SMPS applications. When we look at the market outlook, we see a strong growth in the wide bandgap materials. Gallium nitride shows the strongest growth of the new materials. But as you can also see, even by the end of the decade, all 3 technologies will coexist in the market. We therefore believe it makes a lot of sense to give some examples where to take the best benefits of each technology and to give some insights into topology control algorithms which favor one of the 3 technologies. So my talk will be split into 2 sections. First, I will introduce device concepts and characteristics. And in the second part, we will talk about the value proposition and the positioning of technologies. Taking a look at the comparison between silicon carbide, and gallium nitride from a figure of merit perspective, we are taking CoolMOS C7 as a reference. In the 650 volt class, CoolMOS, CoolGaN, and CoolSiC are all competing. We have offerings of all 3 technologies in the 600 and 650 volt class. On this slide, we are mapping figure of merit to typical switching circuits as shown at the bottom. Let's start with the hard switching at the bottom to the left, where one switch is switching against a diode. That would be like a boost circuit being used in power factor correction stage, typically in the past using CoolMOS switching against a silicon carbide Schottky diode. The relevant parameter in this type of application is RDS(on) times CSS. We assume that we can turn off the switch lossless, and at turn on, the energy stored in the output capacitance is dissipated as heat. The ultimate switching limit would be RDS(on) times CSS, the so-called Nakajima limit. Moving forward into RDS(on) times QG and RDS(on) times QSS, this is irrelevant for half-bridge based circuits, typically operating in soft switching. The LLC would be a very good example out of this class of converter. The gate charge matters, but also the energy stored in the output capacitance, as RDS(on) times QSS is an indicator for the magnetizing current, which is needed in order to remove the charge in a given time frame. If we go into hard switching applications, so half-bridge-based circuits switching in a hard manner, like a totem pole, a bridgeless PLC circuit operating in continuous current mode, here, of course, the RDS(on) times QRR, the reverse recovery charge, is the parameter which matters most. In the parameter reverse recovery charge, gallium nitride excels with 0 reverse recovery charge, as there is no blocking p-n junction in the structure, but also silicon carbide is factor 50 lower than superjunction devices due to the very short ambipolar lifetime of electron-hole plasma inside the silicon carbide MOSFET. In the parameter QSS, gallium nitride is definitely the best technology, which recommends gallium nitride primarily for high-frequency operation. And on the very left side, the RDS(on) times ESS, that is a parameter where CoolMOS is nearly on par with gallium nitride and silicon carbide. And in moving the technology forward, moving from CoolMOS C7 into CoolMOS C8, RDS(on) times ESS will further go down and will bring basically the switch into the ballpark of gallium nitride today. Let's take a look at the switching losses. So at turn-off, as I mentioned on the previous slide, it's important that you come in terms of switching losses very close to the R1 times ESS limit. That is the dashed line, which you see on the diagram. And you see that with superjunction devices, due to the strong non-linearity of the output capacitance, we can basically turn off the channel before the voltage rises across the switch and come very close to this fundamental switching loss limit. But also gallium nitride excels in this parameter. I show here a measurement from the legacy GaN systems technology, which is a Schottky gate-based gallium nitride device, which is also extremely close to the RDS(on) times USS limit. Now moving forward into half-bridge-based circuits, superjunction technologies have been optimized for hard switching. You see the dark shaded green area on the top left of the diagram that represents the energy stored in the output capacitance. And by optimizing that technology, we are pushing this parameter ever more into the top left corner, reducing the energy stored in the output capacitance generation by generation. If you compare this with gallium nitride has roughly the same energy stored in the output capacitance, but the QSS, as we've seen in the previous table, is more than a factor 10 lower. And that means in half-bridge-based circuits, where losses are not only dominated by the energy stored in the output capacitance, but also by the losses created by the QSS, which basically flows as load current through the device turning on at typically a voltage level close to the DC link voltage. That is also creating a lot of losses. And here gallium nitride is significantly better. So hard switching, half-bridge-based circuits, gallium nitride and silicon carbide both would allow to do so, whereas in superjunction devices, this can only be done in case of abnormal conditions for a few cycles. And here, ideally, only in technologies having a fast body diode. Moving forward, when we compare the device concepts, we see that the zero reverse recovery charge allows significant reduction of the losses, especially in half-bridge-based circuits. And moving forward, we'll talk about this a little bit later. Gallium nitride as a lateral device technology further allows the integration of additional functions and also the creation of bidirectional switches. So summing up, basically, we are seeing a coexistence of all three technologies. Gallium nitride with Schottky gate, we're using in the low to medium voltage range, 100 volt and 200 volt, and with the acquisition of GaN systems in the 650 volt. The gate injection transistor technology we're using in the 600 volt, and we're looking into potential expansions into higher voltage classes. And silicon carbide, which is basically available from 400 volt, 600, 650 volt, 750 volt, 1200 volt, and so on, ranging into high voltage applications. As mentioned, all three technologies share the market. Gallium nitride we position primarily in the high frequency domain and primarily in soft switching applications, whereas silicon carbide we see as a very suitable technology for high power applications, for applications which are doing hard switching at low to moderate switching frequencies. Let's go ahead into the value proposition and the positioning of technologies. The typical architecture for a server power supply consists of a power factor correction stage, followed by an isolating DC-DC stage. In the power factor correction stage, we are seeing coexistence of several topologies and control algorithms. We're seeing a big portion of the market moving into the totem pole. Within the totem pole, we see hard switching, but also soft switching applications, so-called triangular current mode modulation, which would be suitable for silicon superjunction, but which would also create a lot of benefit if taken into very high frequency applications with gallium nitride. In continuous current modes or hard switching at typically low frequencies, 40 to 60 kilohertz, we are seeing primarily silicon carbide. In the LLC, we are seeing typical switching frequencies in the range between 100 and 400 kilohertz. In the low frequency domain, so 100 to 150 kilohertz, there is still a lot of usage of silicon superjunction devices. And then towards the higher switching frequencies, we're seeing a clear value proposition of silicon carbide, but especially for gallium nitride. Let's start with the power factor correction stage. We recently demonstrated a 3-level PSC stage, achieving 3 kilowatt in half a U height. The height of this demonstrator is only 22 millimeter. We can stack 2 of these boards in order to reach 6 kilowatt power, which clearly supports the trend in server power supplies to move from around 3 kilowatt into 5, 6, or 7 kilowatt in the near future. As the topology is a 3-level PSC stage, we can use lower voltage rated devices. In this case, we're using our brand new 400 volt rated silicon carbide MOSFET. As you can see from the efficiency curve, the topology achieves more than 99% peak. And if we compare this now with a number of different solutions, which we have been demonstrating over the last years, ranging from devices using silicon superjunction, a dual boost topology based on silicon, then a totem pole running on silicon carbide, then a totem pole running on the gate injection transistor technology based on gallium nitride. And then the 2 versions which we are talking about today, using 3-level modulation with 400 volt silicon carbide. One option is to take the PSC stage as it is. A second topic we are working on is to combine it with a power pulsation buffer to reduce the amount of capacitors needed for the hold-up time. And as you can see from this table, all of the topologies achieve 99%, but the power density, especially in a 3-level PSC with power pulsation buffer, is absolutely outstanding, achieving 160 watt per cubic inch. Moving forward, we see a continuous increase in power levels, especially in the enterprise segment, as power levels go up and the form factor of the power supply unit is staying constant, we see a constant increase in the power density from 25 watt per cubic inch into 60 watt per cubic inch, achieving 85 watt per cubic inch and above, coming actually close to 100 watt per cubic inch. So in addition, we need to meet 96% efficiency. That is mandatory in Europe, the so-called titanium level efficiency. So if we now look into solutions based on silicon, we are seeing that at around 70 watt per cubic inch, they are reaching a tipping point where silicon-based designs no longer can meet both titanium level efficiency as well as the required power density. So if you move beyond 70 watt per cubic inch in terms of power density, we see a clear value of wide-bandgap devices, typically silicon carbide in the PFC stage and the total pole, and gallium nitride in the LLC. Along these lines, we have demonstrated a very high power density DC-DC stage, achieving an outstanding 345 watt per cubic inch. We have demonstrated an ultra-compact DC-DC converter consisting of a matrix transformer structure where the power is split between two boards being stacked upon each other, and the matrix transformer is constructed in such a way that it connects the two boards into one magnetic structure. We are combining this demonstrator with a range of modulation schemes. We are using classic LRC control with variable frequency. We are then moving into boundary mode, and eventually, in order to limit the high frequency operation, for example, at very light load or during startup, we are actually using a 3-level modulation to ensure that the effective switching frequency is never moving beyond 700 kilohertz in this case. By combining the two boards, we achieve an outstanding efficiency of more than 96%, close to 97%. And as you see from the loss breakdown, the transformer loss and the synchronous rectification losses are the two primary sources. On our side, we can further optimize the losses in the synchronous rectification part, so especially the very precise control of the dead time in order to avoid the diode operation of the synchronous rectification switches is a key in order to further optimize this demonstrator and to bring it finally above 97%. Moving forward into a very new chapter of power devices, I'd briefly like to touch on bidirectional switches, the switches which can block voltage in both polarities and which can conduct current in both directions. A lateral device technology like gallium nitride offers to use the same drift region to block voltage in both polarities. So rather than having to series connect two devices, which would double the addison, and then putting another two devices in parallel to come back to the original addison, which means your amount of devices and the cost increasing by factor 4. In gallium nitride, we can just add one more gate line and can use the same drift layer to block voltages in both polarities. So the bidirectional switch is a topic which is perfectly playing to the strengths of the material system in gallium nitride. And as you see on the right-hand side, we have now two gates being referred to the two load terminals. So electrically, this would basically compare to a common drain arrangement of two switches, but actually it is one monolithic integrated switch blocking voltage in both polarities and conducting in both directions. What the technology allows to do, it allows to combine power conversion into a single stage. Rather than having a separate power factor correction stage and a separate isolating DC-DC stage, we are operating an isolating stage directly from the AC grid. So we combine the power factor correction and the isolating DC-DC stage into one single power conversion. That requires AC switches which are able to block voltage in both polarities of the grid and to conduct current in both directions. Gallium nitride, as mentioned before, is the perfect technology to do so. Looking into academic achievements, there are two interesting references. Basically, the work from Jauch, who was doing his PhD at the Institute of Professor Biela at the ETH Zurich. He was investigating basically a type of cycloconverter in a single-phase setup, and more recently, Lukas Schrittwieser at the Institute of Professor Kohler, also at the ETH Zurich, investigated a three-phase isolated matrix-type dual-active bridge, achieving an outstanding efficiency of around 98%, and using basically single-stage power conversion directly from the three-phase AC grid into a 48-volt output voltage. In terms of control options, there is, on the one hand side, the dual-active bridge control by Lukas Schrittwieser. There's publications on cycloconverter control from the Institute of Professor Perrault at the Massachusetts Institute of Technology, for example, the PhD of Brendan Pierre. And there's also state-of-the-art from SMPS, like figure 7 shown from the patent of Ngo et al. So all three control techniques can be used in single-stage power conversion. And on the right-hand side, I show again the topology by Lukas Schrittwieser, where now basically the two switches would merge into one single switch, a bidirectional AC switch made out of a gallium nitride based technology. Summing up my talk, we see a clear coexistence of silicon-carbide and gallium nitride based technologies. Silicon carbide we see primarily in hard switching applications up to switching frequencies of around 100 kilohertz. Silicon carbide comes with outstanding ruggedness features such as short circuit capability and avalanche capability. It's primarily used in the 1200 volt class, but expanding towards higher voltage classes and also being used in lower voltage classes at 600 volt and, as mentioned, even down to 400 volt. Gallium nitride is a clear technology for the ultimate power density. We have demonstrated soft switching up to a megahertz. We recently built a PSC stage consisting of 3 interleaved phases with an effective switching frequencies of 1.8 megahertz. It allows integration of features and it allows the creation of bidirectional switches. Primary voltage classes in the 600 volt range, but also in the middle voltage range, 200 volt, 100 volt, and potentially lower. As mentioned, Infineon believes in the coexistence of these two wide-bandgap technologies. They are rather complementary than competing, and they are, as I discussed in my talk, also very nicely complementary to our offering in silicon technologies. That brings me to the end of my talk. Thanks a lot. I'm very happy to answer your questions.
Well, thank you, Dr. Deboy, for that interesting presentation. It's really exciting to see what's happening in the world of wide bandgap semiconductors. So, audience, there's still time to ask questions. We've got a pretty good queue lined up here, but there's still time to send those in via the Q&A chat box on the right. So, you ready to answer some questions?
Yes, I do.
All right. The first one is asking an interesting question here is, will there be a space in the market for silicon technologies in the mid to even long run, or will wide bandgap technologies really take over for the power market entirely?
Yes, so from our market model and also looking into the figures of Yole, which I cited at the beginning of the talk, we are seeing a coexistence of all technologies, at least for another decade. Even so, the growth rate of silicon carbide and gallium nitride is much steeper than the overall growth of the market. Silicon remains as an important pillar in the overall product mix and technology mix to serve the entire market.
And I think I'll just follow up on that one. Is some of that, you mentioned that gallium nitride and silicon carbide are ramping up faster than the overall market. Is that just because the volume of availability is going up and that the scaling is driving the cost down to make it more cost effective in some of these applications?
Yeah, I think there are a couple of factors. On the one hand side, the technologies, especially silicon carbide, have gained maturity. They are available from a number of sources in the market. Gallium nitride is now just, I would say, at the hockey stick point where volumes really go up, starting in the consumer domain, of course, but basically getting traction in quite a number of cases. And therefore, there is a good momentum to bring silicon carbide and gallium nitride in higher volumes into the market now.
Excellent. This question is a good one here. I like this. This is from a student. He's asking, what is the best way to hands-on learn about the latest technologies? And really in the academic world, power transistors are not a real big focus. So that's a really challenge. So how would you help a student out in that regard?
We are giving tutorials at the university, and there are a couple of demo boards which can be ordered through our ordering system, where I think for a student, it's always best to learn hands-on, getting familiar with the board, getting familiar with the technology, and demo boards which are designed to have easy access to measuring points are the best way to do so.
Thank you. All right. This is kind of a follow-on, I think, of an earlier question, but have silicon-based technologies already reached the end of their roadmap?
Yeah, not yet. We are just launching our CoolMOS C8 technology, and C8 in comparison to the previous technology is still a significant shrink of the cell. So basically transistors also in the 8th generation become better and cheaper at the same time, thanks to the shrink. So the technology enables further advancements in the technology with more refined processes and always pushing the envelope of even better devices, lower area-specific on-state resistance, lower figure of merit QSS, and gate charge. And of course, bringing more dies per wafer is lowering production cost.
Now, this question is interesting because we kind of group wide bandgap semiconductors, kind of talk about them often, globally. But do you see silicon carbide and GaN competing for the same sockets, or do you see the technologies more complementing each other?
They are rather complementary. So, of course, in the 600 volt, 650 volt class, we are offering both technologies. We are now expanding also with silicon carbide into the 400 volt space, because the overlap is getting a little bit larger. But overall, I see the technologies rather complementary than fighting for the same sockets. Basically, silicon carbide spanning from 400 volt, 600 volt upward into 1200 volt, 1700 volt up to 3.3 kV. Gallium nitride more towards lower voltage classes, down to 100 volt and lower. Gallium nitride being optimized for very high switching frequencies. Silicon carbide more for lower switching frequencies, but coming with intrinsic ruggedness, vertical transistor, high voltages. So they are, besides the 600 volt segment, where all three technologies can be used. That was exactly the topic of my talk, to bring a little bit, let's say, clarity and a little bit guidance into the 600 volt class, where you really have all technologies available. But overall, it's rather complementary.
Okay, excellent. This person's asking that they heard Infineon is launching a 400-volt SiC MOSFET. What application fields do you see for these new products?
One of the interesting applications, which I mentioned also in the talk, is the multi-level PFC. We're seeing power levels in high power SMPS going continuously up. Artificial intelligence is driving higher power for server power supplies. And so you need to get smaller in the passive components. Multi-level is an obvious way to do so. Like I showed, the 3-level PFC, outstanding efficiency and outstanding power density, most in factor 2 better than 2-level. That is one of the areas where we position the 400-volt silicon-carbide MOSFET. More to come on PCIM in Nuremberg next month.
Yeah, so you can join Dr. Deboy and I at PCIM coming up here shortly. This question, in which application segments do you see the strongest growth for GaN-based technologies?
So for the time being, the strongest growth is in the consumer segment, chargers, adapters. That is carrying the market at the moment. But we see also starting traction in server and telecom power supplies, both in the PFC stage. Totem pole topology would be a classic application, and the applications towards DC-DC converters or LLC running on higher switching frequencies. That is one of the areas. And the third field, more for the future, are the automotive applications. Here, the onboard charger and the DC-DC converter converting power from the high voltage battery down to 48 volt or 12 volt.
Okay. So you talked about the semiconductors that kind of go inside these products, but could you also talk a little bit about the importance of the advancements in packaging technology for power semiconductors?
Yeah, we've shown, for example, I think 3 or 4 years back, that gallium nitride can switch up to 500 volt per nanosecond. So ultra fast. Superjunction devices have been switching at 50 volt per nanosecond and 100 volt per nanosecond. Now the latest generation may be 200 volt per nanosecond. So the parasitics of the commutation cell and the layout of the board become ever more crucial. I talked in my presentation about reaching the so-called Nakajima limit, which means you come in turn-off loss really to the energy level of the energy stored in the output capacitance. That requires that you turn off the channel faster than the voltage can rise across the switch. Then you're exactly at this point, and that requires that you're not limiting the turn-off process. As soon as you start to limit the IDT and the VDT at turn-off losses go up with the square of the load current, and then the efficiency and the benefit of the latest technology starts to go down.
Now, this question is kind of the opposite of one you answered just a little bit ago, saying where the applications are, these silicon carbide and GaN are being used. But this one's kind of the other one is, which of these applications are really driving most of the innovation? Is it EVs, data centers, or something else?
Yeah. So the data centers, and here specifically artificial intelligence, they are driving heterogeneous integration, bringing power stages together with inductors, mainly for very low voltage, high current applications. So powering the latest generation of processors, we're talking about thousands of amperes at 0.7 volt. So that is the field which is driving integration and packages. On the other end of the applications, like EV charging, the external EV charging is, I would say, uncritical. But if we go into the onboard charger, so where size and weight really matters, here power density, good efficiency as it is part of the overall electric efficiency becomes important. Furthermore, additional functionalities like bidirectionality, like vehicle to load applications, where you power your home, you power your air conditioning system in case of a blackout. But these things become more important. State of the art today is 1.5 kilowatt per liter. We've shown that with gallium nitride, we can push power density to 10 kilowatt per liter. We took a Vienna rectifier-based design into more than 500 kilohertz switching frequency. And looking forward into the bidirectional switch, now you can do single-stage power conversion, which is specifically interesting for the onboard charging market. So in the future, we may see single-stage power conversion connecting on the one hand side to the three-phase AC grid, and on the other side directly to the high voltage battery, combining power factor correction function and isolated DC-DC conversion into one stage. So interesting aspects, no doubt. So stay tuned. There's a lot more to come in terms of new technologies, driving new applications, and vice versa. So deriving new technology out of specific requirements from lead applications.
Yeah, wow. Those are some demanding requirements. So it looks like we've covered all of our audience questions. Thank you again, Dr. Deboy, for that great presentation, this Q&A. Do you have anything else you want to elaborate on or want to make sure our audience takes away from this session?
Yeah, so as mentioned already in the title, we believe in the coexistence of all three technologies. Silicon carbide and gallium nitride are growing at a much, much faster pace. Especially gallium nitride is offering new applications, new solutions. And here specifically to mention the bidirectional gallium nitride switches, which can create single-stage power conversion, which can pave the way into, for example, current source inverters instead of voltage source inverter for motor drive. So it's an enabling technology. It's not just a replacement, but it's together with the right topology, with the right control algorithm, it's opening up a new space of applications. So stay tuned. Future is going to be very fascinating with respect both to technology and applications.
We had a question come in, so just under the wire here. It's asking, could we increase the range of an EV vehicle by using silicon carbide or GaN or any other elements?
Of course we can. So there are two topics to mention. Topic one is the main inverter. So getting the main inverter to higher efficiency helps with the range directly. This is what drives the application of silicon carbide MOSFETs into the main inverter. Then in a second step, you could think of bringing the ripple within the electric machine further down. So rather than going with 20 kilohertz in a 2-level modulation, you go for 3-level modulation with the machine. That ripple that reduces the ripple in the machine and improves the efficiency significantly. So these are the two major items. Then, of course, getting the charging more efficient helps with the overall footprint, the carbon footprint of the electric car. But for the range, it's primarily to optimize the main inverter, and here specifically for driving profiles at low speed. And here's the silicon carbide MOSFET having an ohmic characteristic, not a threshold like an IGBT, is having significant advantages. I think studies shows that with the silicon carbide inverter, you're gaining like 7% in the range of the VLPT drive profile, which is quite a lot.
Quite a lot. Well, thank you so much. I appreciate you coming and joining us for this session today.
You're welcome.
Before we wrap up, I'd like to announce our giveaway winners for the session. 2 winners will receive an event t-shirt and wireless charger, courtesy of Mouser Electronics. Congratulations, Tom Hamilton and Jose Samaniego. We'll be in touch with you within the next week to ensure we have the information we need to send you the giveaway package. Thank you for attending EE Power Day 2024. In a moment, you'll be redirected to Infineon's exhibitor booth. I encourage you to check out today's keynotes, live sessions, and published content. Thank you.